Hi, welcome to AB Video 3.3b Part 1, more on the first derivative test. Okay, so now we're looking at exercises 43 through 50. It says consider the function on the interval from 0 to 2 pi. So these are all going to be trig, which is going to make them a little trickier. For each function, same old question, find the open intervals on which the function is increasing and decreasing. Notice they're not reminding you need to find the critical numbers anymore. It's automatic. And apply the first derivative test to identify all the relative extrema, and then, of course, use your calculator to make sure that you got the right answer. So this is like number 44. Here's your f of x. Your domain, of course, all real numbers. Your vertical asymptotes, none. Critical numbers, you're going to find the derivative. It is a product rule, so you'll use the product rule. You'll get cos squared minus sine squared, which, by the way, is cosine 2x. Okay. Another way of looking at it is if you know the formula that the sine of 2x is 2 sine x cos x. Well, sine x cos x is a half of 2 sine x cos x, which makes it a half of sine 2x. If you notice that, it's way easier. Then the derivative is 1/2 times the cosine of 2x times 2. The 2's cancel. You're left with just cosine 2x. So the question is, when does the cosine of 2x never exist? Not exist, never. When does it equal 0? Now, cosine is equal to 0 here and here. So that means, and again, they did give us an interval. We're only interested from 0 to 2 pi. So from 0 to 2 pi, the only ones that would happen. Oh, now, this is a double angle. So I have to go twice as far. So in other words, and I don't think I wrote that anywhere, but let me kind of add this in, okay, on the side here, and I'll do it in purple. And that is, since they want x to be between 0 and 2 pi, okay, then that means your 2x would have to go between 0 and 4 pi. So I'm going to have to list enough angles over here all the way up to 4 pi so that when I divide, I'll get answers that are between 0 and 2 pi. So I have plus or minus pi over 2, 3 pi over 2, 5 pi over 2, etc. I'm only interested in the positive angles. When I divide by 2, I'll get pi over 4, 3 pi over 4, 5 pi over 4, etc. So I'm going to take the ones that are between 0 and 2 pi. That's 1 3/4 pi. So I don't have a number line this time. These are my critical numbers, by the way. They're in the domain, which is all real numbers, and they make the first derivative equal to 0. Now, I only have an interval from 0 to 2 pi for this problem because that was said in the thing. We're only looking on the interval from 0 to 2 pi, open parentheses actually on both, so that's an empty dot. Don't forget to label. Now, this is what's hard, is determining whether or not it's increasing or decreasing. You can't use even though the signs alternate, you can't use that very much. So this would require you to realize that if you take 2 times any angle between 0 and pi over 4, then 2 times pi over 4 would be pi over 2. That'll give you a first quadrant angle, so that'll be positive. If you take an angle between pi over 4 and 3 pi over 4 and double it, you'll get pi over 2, and double that is 3 pi over 2. Well, that whole time, the cosine is negative. So you go through that process. It's tedious. And of course, when the first derivative is positive, f is increasing. When the first derivative is negative, f is decreasing, etc. From left to right, if it goes from increasing to decreasing, there's a relative max. If it goes from decreasing to increasing, there's a relative I wrote that down wrong. Let me fix that. Okay. Okay, so for 3 pi over 4, it goes from decreasing to increasing, so there'll be a min, and here it goes from increasing to decreasing, so there'll be a max, etc. So you have relative maxes at pi over 4 and at 5 pi over 4, and relative mins at 3 pi over 4 and 7 pi over 4, and then you'd have to plug those into the original function to get the y coordinates. I know this is a TI-89, but just so you can see what this function looks like, You can here's a max, here's the min, here's the max, here's the min, and those are the exact ones that we found. Okay. 51 to 56, use a computer algebra system to differentiate the functions. Sketch the graphs of f and f prime on the same set of coordinate axes. Now, what they want you to do, which they're not very clear about, they want you to use those graphs to find the critical numbers of f in the open interval, and then find the intervals on which f prime is positive and the intervals on which it is negative, and then compare the behavior. Okay, so obviously you want to use your calculator to find this derivative. So here's number 52. The whole thing's done on the calculator. So here's the function they give you, and here's the interval they give you. So we're going to start by the first question says, find the derivative. We're going to do that on the TI. So if I do that on the TI, I'll get, well, I'm just graphing that. This is just the graph of f right now. I didn't do the graph of f prime. Okay, so if I find the derivative, it'll give me this on the calculator. So in part B, so I graph the original function f of x, which is this red function, and then I'm graphing this function right here. Of course, I could enter it as just the derivative of f1 of x, but they did want to know what the derivative was. So here's the graph of f prime. Now, so here's how you could enter it, right? The key thing is this. Remember what a critical number of f is. It's a number in the domain of f, and right now we're fine. We're on the interval from 0 to 5. Doesn't appear, and you could check it out. It's fine. But a critical number is what makes the derivative f of x, f prime of x, equal to 0 or undefined. Looking at this graph, there is one place that this green graph is equal to 0, where it's on the x-axis. So the one place where it's equal to 0, which you could find the 0, you can do that on the graph of f prime. Put the cursor on f prime, and you'll be able to find the 0 of that function. And you'll notice, and this is going to be later, it's going to be really important, that when the derivative is equal to 0, if you follow up here, you'll notice that's where you have a horizontal tangent line. Of course that's true, because if the first derivative is 0, then the slope of the tangent line is horizontal at that x value on f of x. Okay? And that's the end of video 3.3b, part 1.